Alright, so today I want to go over recursion in Rust. Mainly because when I first started thinking about it, I was a little confused of how everything would work, because Rust has a lot of rules. But I found some resources that cleared everything up for me and showed me exactly how it's done. And I would like to share those. Let's get it. Alright, so let's start off by figuring out what recursion is, defining it so everybody's on the same page. On Wikipedia, the computer science section, it states that in computer science, recursion is a method of solving a problem where the solution depends on solutions to smaller instances of the same problem. And I don't know if this is big enough, so I'll make that a little bit bigger. Cool. So just that statement there alone just means that you can have your problem, and then that problem can be broken up into a sub-problem that follows the same rules as the original problem. That's really abstract in terms of definition, but there are examples and they clear some things up going down the line. So here in the recursive function and algorithm section, they state, a common computer programming tactic is to divide a problem into subproblems of the same type as the original. Solve those subproblems and combine the results. This is often referred to as the divide and conquer method. Alright, so here they go a little bit more in depth, and they state that they divide problems into subproblems that are the same type as the original. So like they were saying earlier, a problem can be divided into a subproblem that is of the same type of the original one, yes? And they're saying that you can solve those subproblems and then combine the results. So if you solve all of these subproblems of the real problem, you will eventually get the solution to the real problem. That is still a little abstract. But coming down here, they continue onward, saying that a recursive function definition has one or more base cases, meaning inputs for which the function produces a result trivially without recurring, and one or more recursive cases, meaning inputs for which the program recurs, calls itself. And they give an example. But let's go back to this statement. Here, a good portion down the page, they finally introduced the idea of base cases and recursive cases. So a lot of times, a recursive function will break problems into subproblems, as in recursively call itself on these new subproblems until it reaches a base case. And a base case is the stopping point for which the recursive step will end and then return a value to go up the stack and then start solving all of the previous subproblems. So the example they give is factorials. And they state it here, but it's easier seen down here. So for a factorial, you can define it this way recursively. Here's the function. Here's the base case. If n is equal to 0, this is your base case, return 1. If n is not equal to 0, do n times factorial n minus 1. And you do this over and over and over again until you reach this base case, and then everything just starts bubbling up. So then you have 1 times 2, 2 times 3, 3 times 4, all the way up. So this is easy to write in any language, but the resource I wanted to show, or I want to show, is Rosetta code. So Rosetta code, and let me move this to the side a little bit so I'm not blocking it. So Rosetta code is, at least in my words, a site where you could view problems solved in many different languages, and they have a large problem set. You could search by the problem set, or you can search by the language. And I typically search by the language because right now we're in Rust and we want to understand how things are done in Rust. So you can search for the category of Rust and it gives you some descriptions, but down here it has the problem sets, all of them listed. And right now we can do factorial, and you can click on it, right? And it'll bring you to the problem set of factorial. It'll define what the problem is, what the task is, and then it has a list of the languages that were used to solve this task. And the list is typically really long, so you could do a search for Rust and then click on Rust. Make this slightly smaller. Alright. So here in the addition of Rust, here, that's big enough. We can see how somebody went about solving the factorial problem. And they did it in a number of ways. They did it recursively, and they also did it iteratively using iterators. I thought this was powerful because once I saw how somebody else solved the problem, I realized that in terms of recursive problems, you can solve them within a match statement. And given that a match statement is going to make sure that all of the cases are, all of the possible cases have a arm, I think personally that might make writing recursive functions easier. So in this case, we have the base case of the factorial, which is if n is equal to 0, return 1. And then for every other instance of n, denoted by the underscore, we do the recursive step, which is n times factorial underscore recursive, name of the function, n minus 1. Understood. And if you want to see that iteratively, they did n, or 1 to n dot product, and that returns the same thing. Cool. Another problem that is typically used to exemplify recursion is the greatest common divisor problem, which is how you find the greatest common divisor between two numbers. And here's how it's defined, right? We have x and y, given that they are, I guess, integers. Does it work for floats? I don't think so. I think they have to be integers. Not sure about that. Anyway, we have the base case. If y is equal to 0, return x. Otherwise, do GCD y remainder xy. And if you note, x starts at the position here and y is here, second. But when you get to the iterative step, the recursive step, y moves to where the x was, and the remainder, or the modulo, is what's put into the y position of like the original definition. Great, you can write that out pretty easy. And if you wanted to see an example of that, they had that on Rosetta Code as well. So they did it iteratively, so you can see how it's done that way, but they also did it recursively. This time they did not use a match statement. However, if you look at the way it's written, we have an if statement. If m is equal to 0, do this, else do this, which could easily be written as a match statement, where match on m, if for the first time, could it be m is 0, do this, and then underscore, for all other cases, do this. Different flavors how you write it. Both are valid. So coming back to recursion again, they have another example, a famous example, the Towers of Hanoi. And if you want to see how it's done in Rust, wait, where is it? I changed the sizing. Here we go. Bam, there's an example of that as well. And it's translation of the C code, which that's also an option. If you don't see a Rust solution, you could look at a solution in another language that you're more familiar with and then translate it to Rust. That's perfectly fine as well. So here, if we take a look at how they did recursion in this example, we see that there is no match, there is an if, there is no else, implying that if this condition is not true, just return, which makes sense. And they just print something. There is nothing being returned at all. This function itself doesn't return anything, where in the previous ones, we always return like an integer or something like that. Factorial, where did it go? Rust. So it should be noted that recursion doesn't always have to return something. Sometimes if you just want to act on something, this is the way of doing it. Just print out information. Another example, well, another problem that is typically used to exemplify recursion is binary search. And Here, I'm showing this one mainly because I didn't realize this was a thing in Rust, but the standard library does have a binary search function for you, so you don't have to write it. I just thought that was interesting because going through other people's solutions allowed me to learn that I didn't have to write the solution. I don't have to write the solution ever in Rust. It's there for me. I did look at their implementation for a bit. I don't believe it is recursive, but still, solves the problem for me. And here you can see an iterative solution. I didn't really walk through this. I just know that it existed, and I can see it as an example. Alright, so one thing I did think was cool was something I haven't really done in recursion before, and it's mutual recursion. So I think that's defined here as well. Let me find it. Mutual recursion. In mathematics and computer science, mutual recursion is a form of recursion where two mathematical or computational objects, such as functions or data types, are defined in terms of each other. Mutual recursion is very common in functional programming and in some problem domains, such as recursive descent parsers, where the data types are naturally mutually recursive. So this statement seemingly means that you have one recursive function that is dependent on another recursive function, and they have been coupled. An example of that does exist in Rust, and I need to scroll down. So let's go back to the top of this document before we dive into what the Rust is doing. They give us the definition of what this is, and they tell us where it's from. This thing, which I cannot pronounce. But we have these two different sequences, and we have the base cases. For f of 0, return 1. For m of 0, return 0. And then we have the recursive definition, which includes each other. So f of n is defined as n minus this m function, f of n minus 1. So we have the internal recursion here, and then we can look at m, which is also defined recursively. So we have the recursive function for the other function there. More or less, f is defined with relation to m, and m is defined in relation to f, and both of f and m are recursive. So coming down to the Rust example, Rust. If you want to see how something like that is implemented, it's here. They just did it in a simple match statement, and it looks pretty straightforward. It looks almost exactly like the definition. And this is the output. So I thought that was cool. Alright, so one last thing I'd like to show before we end the video is an example of using recursion in something that is depth first. And if we go to the problem set, right? We go to trees. What is it called? Tree something. Tree traversal. Cool. More or less, they want us to be able to traverse the trees in order, pre-order, post-order, level order, yada, yada, yada. That is not the part I care about for this example, or at least for what I'm trying to demonstrate. What I care about is how they went about inserting the stuff into the trees, and you'll see in a second. So if we go to the Rust section, we can see here that they defined a tree. It's just an example of a recursive data structure, by the way, because the data structure is defined within itself. So tree, option, box, tree, node, this is a tree node, tree node within a tree node. It also should be noted that they're using a generic T, which I thought was pretty cool. They define their enums for order, pre-order, post-order, yada, yada, yada. That's there. But it's this implementation of new that I really enjoyed. Well, to understand that, you should look at the main real quick. So in main, they take an array, a nested array, that is describing the tree order. if we go to the beginning of the page, we see that this is what they're trying to mimic. They're trying to create this tree structure where 1, 2, 3, 4, 5, 6, 7, 8, 9. And these are the orders that they want to print out, right? So go back to the Rust section. In new, what they do is they do a match on the first item, well, not the first item, the second one in the new array. And they say if it is none, or if it is -1, then that is their base case for returning none. Because if you recall, a tree node is an option, so it's either some or none. And if it is not none, they take the number that is associated with this placeholder and they move it in right here. So we learned this in the, I guess, the advanced section of doing matches. And then you do sum box new tree node, and they're defining the tree. And let me move over a little bit. Can I? All right, we can see everything now. So as we stated earlier, we have -1, which is the base case. We're going to return none. And then here we have the recursive call. We have new, and this is new. So it's new calling new. It's going to come back here. And it's stating that for every other case of whatever this item resolves to, we're going to, I guess, I forgot the exact term, but make sure we can pass that number into the arm. And this we learn in the advanced section of matching in the Rust book, so it's there. So this I gets passed in so it can be used. So you can see the I here. And then we have sum, box, new, tree node, yada yada yada. And then we have the array and the arrays of reference. So it's referencing the same array that has been used here. And then we're going to look at the index of I minus, and he did -0, 0. -0, 0 is a constant. So they didn't necessarily need to put that there, at least not for this example, but it's important to know what this resolves to. And we go down here, back to main, we see that 0, 0 resolves to 1. So coming back, we see that this is I minus 1 as usize, and that's going to be passed back in. And coming to the top of the match statement, we know that this is L, probably for left, this is R for right, and right does the exact same thing, with the difference of it looks at the right side, so the position 2 of the internal array. And it returns the tree node as the initial value for the middle, which is 1, the start of the tree. And it adds left and it adds right. So let's go and look through this. Alright, so I'm not sure if I'm doing this right because I'm spitballing it, but we can take a look at these numbers, right? The first one seems to indicate the node, like there's nodes 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this index seems to be the left node, a reference to it. And this seems to be a reference to the right node. And we can note that by going all the way back to the top and looking at this diagram again. So we see that 1 has 2 on the left and 3 on the right. And just to verify, we can note that 4 has, or 2 has 4 on the left and 5 on the right. So let's go back to the Rust code. And we see 2 has 4 and 5. So now we have a basic understanding of what this is holding, okay? So in terms of the recursive calls, on the first, I guess, iteration, the first run through, we look at this node. This node is going to look at the left side first, which is going to show a 2. We're doing 2 minus 1. 2 minus 1 gives us 1. And that number is important because that is the index for the 2 node. So the index starts at 0, 1. Okay? So in the recursive call, we go from this node to, and then we start looking at this one, and we look at 4 because of the process starts over again. We're starting the function call. We're starting the function call from the beginning again. So 4 minus 1 is 3, which is the index that brings us to here. Same thing we do with 7. At 7, we hit -1. Now, if you remember, -1 is the base case. And if we go back up, we can see that here. So if we hit the base case, we have none. And it's not recursive, so we don't start over again. Instead, we move on to the right side and do that match. And in that case that we just looked at, I think it's 7, -1, -1. So both of them are base cases. So coming back up here, return none for that side, okay. And then we create the node. So we come here. The current 0 for this location is 7. It is the first item in this node. So that value is going to be put here, and then we're creating the left. The left side goes on, and then the right side goes on, which in this case are both nuns. Then we hit the end of this call, and then it recurses back up the stack. So when we're here, we just created this node, and now we can go back up to this one. So 7 has now been defined as a node. And then we're going to look at the right side. So coming up here, we just finished defining this recursively. It's come back up the stack. We have the 7 tree node on the left. And now we're going to do the right side, which had the base case of -1, and then we're defining that node. And then we're going back up the stack again. So here. So now we're going here, and then we're going down the 5 side. And 5 has a left and right. We just continue this process until the entire tree has been filled. I thought that was powerful because there's not much code here. We see the array stuff, and we see this. This is all it took to create a tree. So earlier I mentioned that this is depth first, and the reason why I stated that is, well, you can kind of see it. Depth first goes down a tree all the way to the end and then recurses back upward. So we went from 1 to 2 to 4 to 7, finished 7, came back to 4, finished 4, came back to 2, went down to 5, finished 5, and then it continues back up. Then it'll go down to 3, do 6, come to 8, complete 8, go back to 6, go to 9, complete 9, go back to 6. 6 is now done, go to 3, no there's no right side, then go back to 1, and then it'll be done. And just in terms of filling the tree. That by definition, at least in my mind, is depth first. So yeah, that's pretty much it. I just wanted to go over recursion, and I wanted to go over the resource I use, Rosetta Code, to look at implementation of things that I understand but maybe don't understand it in a specific language, or if I want to look at implementation that I don't think I can write off the top of my head, things like that. It's a great resource. With that being said, we have reached the end of the video. If you liked it, hit like, subscribe. Outside of that, peace.